Hello, my calculus doing friends. I have some announcements for you guys. I'd like you to turn in your quiz 9 and your quiz 10 on today, on Wednesday. I'm going to send you an email too. I said by the end of class time, but whenever you can get it on Wednesday, send it in to me, please. Both of them, scan them together and send them in. Didn't work out that bad to scan the test, and I think it'll work out to scan these as well. And then we're going to do the video notes on 3.9. We're going to do that next. On Canvas, I've given you the note outline sheet. If you want to print it, you can, or if you don't have a printer and have a way of printing it, you don't have to. And boink, 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 spring break, woohoo, yay, and then doink, doink on for the, so that's kind of how we're going along. I'm also going to get you quiz 11 pretty darn soon. And so anyway, so that's kind of the story there. Here, the homework is on the second page this time, just because so much room was taken. And so it really does work to do the homework. It really helps you learn the material. This is 3.9. It's on antiderivatives. And the book puts the antiderivatives in as an application of the derivatives in the end of chapter 3 and also in chapter 4 and also in chapter 5. So I kind of like them all to be together, and so that's the reason that we're doing 3.9 with chapter 4. And so anyway, so that's today's thing. And so they tell you that that capital F is the antiderivative of f on an interval I, provided that f prime equals f for all x in that interval. And so they're asking us to find the most general antiderivative of the function and check your answer by finding the derivative. And they're going to call the antiderivative the capital of that variable. So they're going to call the antiderivative capital F. And what we're trying to think of is something that when we take the derivative of it, I couldn't say that hardly, we get x to the second. And so remember how when you take the derivative, it comes down in front? Remember how that? Now we're going to go backwards of that process. And then you take away 1. And so if we're trying to go backwards of that process, and remember, you take away 1, it seems like that you would add 1, right, to go backwards. So if I get x to the third here, now when you think about taking the derivative of that, well, you would move the 3 down in front, but that didn't have a 3. And then you would get x to the second. So that was perfect, other than when I take the derivative of this, I put the 3 down in front. So if I want to get rid of that 3 that's coming down there in front, I would just have to divide by 3. And so now find the derivative of this piece and see that it is x to the second. And then I want to do the same thing here. The minus 3 will hold still. And then I'm going to, the exponent is already 1. I'm going to add 1 to that exponent, so that's going to be x to the second, so that if I'm just kind of ignoring the 3, if I take the derivative of x to the second, it's 2x. And now I want to get rid of that 2. I got the x I wanted, right? And so you divide by it. So, and so then the next one, the derivative of it is equal to 2. So that would be 2x. The derivative of 2x is 2. So kind of going backwards here. And then one last thing. I took the derivative of it and got 0. So what was that thing? You're right, a constant. Okay, so there's the most general antiderivative. We just put c for a constant. Some books put k. Some books put c1, c2. Whatever, and so anyway, so that's kind of that story on that. Then I have a place, and they have this table in your book too, for the antiderivatives, and so the first one they call the power rule, and I like to call it the unpower rule, because when we called it the power rule when it was the derivative, and now that we're going backwards, I feel like we're undoing that, and so. Simply, since we're going backwards, you add 1 to the exponent. And then you divide by that exponent, what it is. Divide by the same darn thing is what I like to say. So the antiderivative of x to the n would be this, and then plus some constant c. And then if you have a constant multiple times a function, then the constant multiple just holds still, and then you take the antiderivative, which they use a capital in your book, and so this capital F is the antiderivative of that. And we kind of saw that up there. We did that in that problem. And if you have a sum or a difference, and we did that in this problem here too, you just do the pieces. And so the antiderivative of, some constant C. I'm going to put K here because it's not that same constant. So I'm going to use a different constant. The antiderivative of F is, capital F is what we represent it with, and then it's plus or minus, and then the antiderivative of G. Now each of these came with a constant. So this one came with a constant, plus C. This one came with a constant, plus C2, maybe, C1, C2. And then all together, when I add those two constants together, I get plus C. And so you don't have to, you just put it once. And then the antiderivative of the sign. And so I'm trying to think of something. I take the derivative of it, and I get the sign. And so now when I take the derivative of the cosine, I don't get the sign. What do I get? Yeah, I get that. So I need a negative. So plus C. And then I want to take the derivative of it and get the cosine. So if I take the derivative of sine, I get the cosine. So going backwards. And then when I take the derivative of this thing, I get secant x times tangent x. Do you guys remember what that is? Yeah, secant x plus C. And then I take the derivative of this and I get secant squared, and that's tangent. I take the derivative of tangent and I get secant squared x. And when I take the derivative of cotangent, I get negative secant squared, so I need a negative here. So when I take the derivative of a negative cotangent, I get positive secant squared x plus C. And when I take the derivative of this thing, I get secant x cotangent x. Do you guys agree that it's negative cosecant x plus C? These pretty much have to be memorized in order to be able to use them. I don't see how you could reason them out as you went. I understand that if we knew the derivative of these two, that we could find the derivative of those two, we could find the derivative of the rest of them by reasoning it out. But I'm not sure how you would go backwards reasoning it out. And so I really do think that you need to know them. Now they're asking me here to find the most general antiderivative. This is problem 6 of that function. And you can't find the antiderivative of a product like that. X minus 5 times x minus 5. So what you really need to do is you need to multiply it together using FOIL, or using whatever you use to multiply that together, and then you can find the antiderivative of the pieces. So the antiderivative of x to the second is x to the third over 3. Add 1 and divide by the same darn thing. The 10 holds still. I add 1 to the exponent, x to the second, and divide by the same darn thing, plus, and then the antiderivative of 25 is 25x. And then I need a constant plus a constant. And I would fix up 10 divided by 2 is 5. And the same thing here, you can't find the antiderivative of a division like that. So what we have to do is divide the pieces. And this one has domain issues, and I want to show you something that your book does, and he doesn't do it on all of them. And so, but you'll see it in the back of the book and you'll be like, why did he do that? And so this one, x should not be equal to 0. So then after mentioning that, because in the denominator, we're going to divide this out here. So this is going to be 5 divided by x to the 6, so that's 5x to the negative 6, right? And then when I divide this, that's going to be minus 4x to the negative 3, do you guys agree? Dividing the pieces, and then plus 2. So that the antiderivative here, add 1 to the exponent. So when I add 1 to negative 6, I get negative 5, and divide by the same darn thing, so just the unpower rule. Minus 4, add 1 to the exponent, so that gives me negative 2, divide by the same darn thing. The antiderivative of 2 is 2x. And then this is where your book is like, well, there's kind of two c's here. Let me reduce this up here, and I'll show you what he does with it. There's kind of two c's. So this is negative x to the negative 5th. This is positive 2x to the negative 2 plus 2x. And what he does with the domain issues is that he defines this piecewise defined. And he says there's two antiderivatives. There's this one, negative x to the negative 5th plus 2x to the negative 2 plus 2x plus c1. And that's when x is greater than 0. And then there's this other antiderivative. And that's when x is smaller than 0. And he does it on some of the problems that have domain issues, and he doesn't do it on the others problems. And I'm not exactly sure why, why the difference in his solution. If he's going to really pay attention to the domain issues that you can have. And I asked the person I love the most, Arnie Stewart Andrazian, and he said he probably should be consistent on the whole thing. And there's some information on page 331 with the author talking about the two pieces of and calling it C1 and C2. So if you'd like to go read that in your textbook and check that out, you certainly can. And so I think it's something that becomes more important to you in Calc 2. And so they have a few of them in this section, and then we don't see it again. So it's not a big deal for our class. But I did want to mention that just in case you were doing homework problems and you weren't sure. Okay, so this one here is asking us to find the most general antiderivative. So they called that G and at B. And the antiderivative of 5 is 5v, because the variable they're using is v. And the 3 holds still. And I'm trying to think of something that when I take the antiderivative of it, when I take the derivative of it, I get secant squared. And so, or the antiderivative of secant squared v. And you guys got it. It's tangent v. You're like, I didn't say anything. And then plus c. And so there we have that one. Pretend like you did say something, and you'll feel better, I think, about it. Okay, initial value problems are the other things that they have there in 3.9 for us to solve. And so these equations here that they're having us solve are differential equations, and this is our first time seeing them here in Calculus 1. And you'll see them again in Calculus 2 and Calculus 3, and also in differential equations. Differential equation, and so they pretty much in our class they call them initial value problems. They also call them differential equations. All the kind of the same story. So how you solve those is that I have to find the antiderivative. So they're telling me f prime equals this. So I'm going to find the antiderivative of this, and I'm going to find the antiderivative of that. Now, finding the antiderivative of that means you have to break it apart and not have it as a division. So you have to think of this as x over x to the square root of x plus 1 over the square root of x, right? And so when that's what that derivative equals, and then this is x to the 1. And take away half, right? So this is x to the 1/2 plus, and then this is going to be x to the negative 1/2. So I haven't found the antiderivative yet, but now I'm going to. antiderivative. Do it. So the antiderivative of this is f at x. And the antiderivative of this, I'm going to use my unpower rule, or my power rule. You add 1, you get 3 halves, x to the 3 halves, and you divide by the same darn thing. And you know, when you divide by 3 halves, that's the same as multiplying by 2/3, right? The reciprocal. So I usually am too lazy to write it like that, and I normally just write it as a multiply by the 2/3. I go right for it. And then I want to find the antiderivative of that, so I add 1 to the exponent, and when I do, I get half, so x to the half, and divide by the same darn thing, well, that's the same as multiplying by 2. And then I'm going to add a constant. And someone just texted me, and oh, I'm off my page, darn it. And someone texted me with my comment to them that I thought that we might be back in school soon, and they said, ha. And so I'm not all done yet, but I'm just kind of making more room for my work. Now I need to find C. That's what the initial value problem is about. And they gave me a way of finding C. They said when x is 1, the output is 5. And we can use that to find C. Now x is not always 1. Y is not always 5. This is just something I can use. This is just one point, and I can use that point, but the C is always a constant. So I'll be able to use that point to find my constant. Actually, I can write that work down here. So f at 1 equals 2/3 times 1 to the 3 halves plus 2, 1 to the half plus C. And we know that f at 1, I wrote that and then didn't know why I wrote it, is 5, right? So I'm going to put the 5 in there. So when I do this work right here, 2/3 times 1 to the 3 halves is 2/3. And then that's just 2. So this is 5 equals 2/3 plus 2 plus C. And all I have to do is subtract that stuff to find what C is. So using my trusty handy dandy calculator, or your handy dandy head, whichever one you want to use, I got C is 7/3. And so now I want to tell everybody my answer. So here's where I'm going to have my answer. My answer is right here, except for I know what C is. C is 7/3. So my answer for F is F at, and this is 2/3 x to the 3 halves plus 2x to the 1 half plus 7/3. And there I solved that differential equation. I solved that initial value problem. And we did a lovely job on that. Okay, so that was problem 34. And we found that particular value for C. And so kind of what you're finding with all these C's, and they kind of show, this is a picture out of your book and it didn't come out that clear, but it's a family of antiderivatives because the C could be any value. And so this definitely is a function, right? It's a function, and if I'd had a different initial value, I'd have a different value for C. And if I graphed all of these, they would maybe not have the same shape, but have the same idea, all these different C's that you would get. So anyway, so that's kind of the story there. This is 56, and they ask us to solve the initial value problem. And I just wanted to remind you guys that when you take the derivative of, that the velocity is equal to the derivative of s, and the acceleration is equal to the derivative of the velocity. So what I want to do is I want to go backwards. I want to take the antiderivative. So if I take the antiderivative of A, I ought to get the velocity. So that's what I'm going to do here, is I'm going to take the antiderivative. So the antiderivative of A is the velocity at time equals the 3 holds still, and then I'm thinking, what's the antiderivative of the cosine? So I'm thinking, what would it be? And it's the sine of t. And I always like to make sure that, because I'm better at finding the derivative than the antiderivative, so I like to make sure that when I take the derivative of this, that I get that. Particularly with sines and cosines, I could get it backwards. And then minus 2. And then what's the antiderivative of sine? Well, it's negative cosine. And so that negative cosine of t, that negative and that negative are going to make a positive plus c. And I want to make sure, let me write this again. Plus 2 cosine of t plus c. And when you take the derivative of this, you get, yeah, negative sine, negative 2 sine of t. Wonderful. Okay, now I'm going to use my initial value to find out what c is. So they said that when t is 0, that the velocity is 4. So 4 equals 3 times the sine of 0 plus 2 times the cosine of 0 plus c. If you're having to use your calculator to find the sine of 0 and the cosine of 0, make sure that it's in radians. If you've been having, someone's been using your calculator for physics, they might have got your calculator in degrees, but we almost never have our calculator in degrees in calculus. And so always when you start using your calculator for math, make sure that it's in radians. Okay, so the sine of 0 is 0 and the cosine of 0 is 1. And so this is 4 equals 2 plus c. So that means that c equals 2. So that gives us v at t equals 3 sine of t plus 2 cosine of t plus 2. And then we would do it again. Find the antiderivative. Antiderivative. So the antiderivative of the velocity is the s, which is your distance function. And 3 holds still. The antiderivative of sine is negative cosine. So this is negative 3 cosine of t, making sure, plus 2 sine of t, making sure, plus 2t, plus, and I could call it c. It's not going to be the same value, and if it was the same value, it would be a coincidence, or some people like to call it something different, like calling it d. And so whatever, it doesn't matter. And lovely, they say that s at 0 equals 0, so this is 0 equals negative 3 times the cosine of 0, plus 2 times the sine of 0, plus 2 times 0, plus d. And this goes away and makes 0, but the cosine of 0 is 1. So this is 0 equals negative 3 plus d. And so that means that d equals negative 3. Ooh, d equals positive 3. Donna, silly girl. And now we're ready to say what our answer is. So here's our answer, right? But instead of saying d is 3, instead of saying d, we're going to say d is 3. So we're going to have for our answer s at t equals negative 3 cosine of t plus 2 times the sine of t plus 2t plus 3. And then that's it. And so we did 56 and did a really nice job on it. And I have one more problem to do here for you guys today, and then I'm hoping that you guys are going to be starting to look at some homework. Some of those homework problems are pretty tricky. I'll just tell you that, and so you guys go find the tricky ones and see how you do on them. So this is motion with gravity. Consider the following description of a vertical motion of an object subject only to the acceleration due to gravity. Begin with acceleration equation for gravity, negative 9.8 meters per second squared. And so they say a stone is dropped from the upper observation deck, the space deck of the CN Tower, 450 meters above the ground. Part before part A, find the velocity for all object for all relevant times. So we're going to start off here with a at t equals negative 9.8, right? And if I take the antiderivative, then I'll know the velocity. So I'm going to take the antiderivative, and that's going to give me the velocity, and the antiderivative here is negative 9.8t plus c. And at the moment that I have this object, they said that I just dropped it. I didn't throw it. And so if I just take an object and I just drop it, the initial velocity is 0. Now, if I throw it downward or throw it upward, then my initial velocity will be other than 0 if I do that. But if I just simply drop it, the initial velocity, so what that means that when time is equal to 0, that's my initial time, my velocity is equal to 0. And so I can plug those in to find c. And so if I do plug those in, do you guys agree c is going to be 0? Because I'm going to have 0 here equals 0 plus c. So c is 0. So my equation is this. If I want to put the units on my equation, the gravity was in meters per second squared. And do you guys remember that the velocity then would be in meters per second? Okay, now it asks me to find in part A the distance of the stone above the ground at time t. So at time 0, the distance of the stone above the ground is 450 meters, right? But after 1 second, where's that stone at? And that's what they're asking you here. And they're saying at any time t. So I'm going to have a variable in there. And that distance is, you can find that with s, right? And so if I find the antiderivative of that, then I'll have s. And that's why I had a before question, because now I can just say to you, hey, we need to find the antiderivative of that. Okay, so finding the antiderivative of the velocity is s at t. The antiderivative of this is you add 1, the negative 9.8 holds still, and you add 1, so that's 2, and you divide by the same darn thing, and then plus, and if you don't want to use c, because you felt like you already used c, you could use d. So this is, that's negative 4.9, right? So s. And so now if you're in your physics class, and they give you a formula for finding when you drop something like this and it has negative 4.9 t squared in it, you know where it came from, right? And so anyway, I know that in my algebra class we do these, and my students ask me, where did that number come from? And I say, wait for it, it's coming. And they'll show you where that came from. Okay, so I want to find out what d is. And I know that the initial at time 0, the height of the stone is at 450. And so when you put in t is 0 and s is 450, do you guys agree that you would get that d is 450? So our equation is s at t equals negative 4.9 t squared plus 450, and this would be in meters. And now, at any time t, I could tell you, hey, where that stone is until it hits the ground. How long does it take the stone to reach the ground? So that's what they're asking next. And so think about what would you need to do to find out how long, how much time it's going to take for the stone to reach the ground. So I'm thinking to myself, well, when it reaches the ground, that's when s will be equal to 0. And so I'm going to put s equals 0 in this equation and solve it. So negative 4.9 t squared plus 450 equals 0. And so I'm going to solve that by subtracting 450 and divided by 4.9. Oh, if they'd had 490 instead, it would have come out a nice number. So I subtract that over to the other side, and I divide by negative 4.9. So I get t squared equals, whatever that is, that lovely number. And then I want to take the square root of that. And I don't really have to pay attention to the plus or minus, right, when I take the square root of that, because it's time, and time should be positive here. So I'm going to take the square root of that, and I get, so 30, the square root of 5 over 7, right, seconds. And that's around, I'm going to push S to D here and see what that's around. That's around 9.6 seconds. You know how math people are. We love the exact. We love the exact even if you can't measure the exact while you're out there. That's just how we are. And then what is the velocity does it strike the ground? And so when it hits the ground, how fast is it going? And so this equation tells us all about the velocity. And if you know how long the stone has been since it was dropped, then you'll know how fast it's going at that instant. And there it is right there, right? And so I'm going to put that value in here. So I'm going to find the velocity at that horrible value, 30 square root of 5 over 7, because you know how I am. I'm like miss exact. I'm just going to put that in because I have that already on my screen. Right, there it is. So I'm just going to multiply it by 9.8, and I should have had a negative in there, and so I'll put the negative in here of the answer. So there it is, the exact negative 42 square roots of 5. That's the velocity meters per second. And S to D, that velocity is approximately 9.93. I lost my negative. Could happen to you. Negative 93.9 meters per second. So approximately, that's our velocity. Velocity could be positive or negative. The negative tells you the direction, it's going down. And so if they'd asked me, what is the speed? Speed should be positive. So if they had said to me, what's the speed? Then I would have said, well, the speed is 93.9 meters per second. Oh, I almost forgot to tell you the code word for attendance, right? And I'm going to be sending out an email. It'll come out before Thursday, asking you just to send me back by email these code words, just to make sure that you're participating in the class. And the code word is GOAT. And so that's the code word. I almost forgot. Okay, I hope that you're having a good Wednesday, and I hope that you spend the rest of our class time working homework problems, and I hope that you go to Andrea's session and get some help from Andrea. He's really wanting to help you guys, and he's awesome. And so and I appreciate him so much. Okay, thank you. We'll talk to you later. Bye-bye.